morning, students. Today I will discuss about the basic principle of sedimentation tank. So please come to the topic. So this is sedimentation tank. Now I have already discussed in my previous video that different types of sedimentation tank. Now I will discuss about the basic principle of sedimentation tank. So first of all, you have to know some assumptions in sedimentation tank. So in case of a horizontal sedimentation tank, we can similarly show that the removal is likewise dependent only upon the overflow rate. So the main thing is removal is dependent only upon the overflow rate. Now there are some assumptions of sedimentation tank. So please write down what are the assumptions of sedimentation tank. There are generally three assumptions. The first one is particles and their velocity vectors are evenly distributed across the tank cross section. So please write down the first assumption, that is particles and their velocity vectors and their velocity vectors are evenly distributed across the cross section of the tank. Across the cross section of the tank. The second thing is the liquid moves as an ideal slab down the length of the tank. The liquid moves as an ideal slug down the length of the tank. And the third thing is any particle hitting the bottom of the tank is removed. So any particle hits the bottom of the tank is removed. These are main three assumptions of sedimentation tank. Now please write down, please draw a picture, that is draw a diagram about the sedimentation tank. Suppose this is a sedimentation tank. That means a rectangular sedimentation tank. And this is actually sludge zone of the tank. And from the top, this is actually depth of the tank, and from here it is length of tank. It is the length of the tank. Now, if there is a particle, obviously this is a inlet zone and this is outlet zone. If a particle coming from the inlet zone having the velocity v, then its settling velocity should be vs, that means, which I have already discussed in my previous class. Now, if there is a particle moving like in this direction, so this particle, actually the velocity is like in this way, that is v, and the settling velocity, which is actually vs. And for this criteria, here vs should be greater than equals to v0 for removal of particle, and for this portion it should be vs less than v0, that means there is no removal. So from this triangle, actually inside the triangle the particle should be removed. Now consider a small triangle, that is A dashed, this is the depth of water actually, and suppose this point is A, and I am considering a point that is A dashed, and here it is forming a small triangle, and this point is B and this point is C. And this height is actually small h. This height is actually small h. Then let us consider a discrete particle which enters the tank at the top of the basin at point A. So please write down. Let us consider a discrete particle which enters the tank at the top point A. Now, at full height h from the bottom, at full height, that means the height of the water or depth of the water, h from bottom. Now, such a particle will have a horizontal flow velocity, that is v, and a downward velocity, that is vs. So here horizontal velocity, that is v, and downward velocity, that is vs. Now its resultant path is given by the vector sum of the v and vs, which is actually this direction, and this is actually the vector direction. So its resultant is actually a vector direction. Now this is actually the particle's flow, settling flow. So if this particle entering at the top of the tank is so removed, that means the settling velocity Vs should be greater than equals to V0, and the settling velocity Vs, if not greater than V0, that means Vs less than V0, then it should not be removed. Now, considering the extreme case of slope vector from A to C. Now, considering the extreme slope vector from A to C, then from the geometry of the basin we can write from the geometry of the basin we can write that V by Vs, that is equals to L by H. If length of the tank is denoted by capital L, then V by Vs equals to L by H. Suppose this is equation number 1. So V by Vs, that is equals to L by H. Now put the value in the equation number 1. So what we get? We have got that V by Vs equals to L by H. Now we can write down that from here Vs equals to V into H by L. It is simple. Now for V, that is equals to Q by BH, where Q is the flow velocity, B is the width of the tank, Q is the flow velocity, B is the width of tank, and H is the depth of water. So if we put the value in this equation, then we will get that Vs equals to, put this value of V in this equation, then Q by BH into H into L. So from here we can write Vs equals to Q by BL. So this is the equation, that is Vs equals to Q by BL, or we can write down Q by AS. What is AS? Where AS is the surface area of the tank. That means width of the tank into length of the tank. That is surface area of the tank. And this Q by AS is nothing but it is the overflow rate of the tank. So what are the findings actually? That the settling velocity is not dependent on the depth of the water. So please write down what is the actual findings from this derivation. The actual findings is the surface overflow rate can be said to be representing the the surface overflow rate can be said to be representing the settling velocity of the slowest settling particles. Settling velocity of the slowest settling particles, which are 100% removed. Which are 100% removed. Now, if the settling velocity is less than V0, then in case of lighter particles, the particles entering at the top of the tank should not have reached the bottom of the tank. So this is actually, and for that case there is a partial removal of particles will occur. So please write down a horizontal rectangular clarifier. So horizontal rectangular clarifier will thus cause not only the removal of heavier particles, will thus cause not only the removal of heavier particles, that is particles having Vs greater than V0, that is particles having Vs greater than equals to V0, but will also cause partial removal, but will also cause partial removal of the smaller size particle having Vs less than V0. Okay, so this is the actual findings from the derivation of the settling velocity. Now, if we calculate that how much percentage of the light will be removed from ideal sedimentation tank, then the removal should be, the percentage should be, partial removal percentage should be Vs by V0 into 100%. This is the percentage of partial removal of the from the settling tank. Okay. I will discuss about a design of sedimentation tank with a numerical problem. Thank you.